Okay, good morning, everyone. Uh, okay, so today I will finish the line integral theorem. Uh, get into the another section, which is we call it green theorem if we have time, and if it's sufficient, the curl and divergence. But I think maybe not enough time. Maybe that will be on Monday. And since I think our exam schedule for our school is the first week of June or end of May. First week. Right? Yes. Okay, so first week of June we will have a final exam. But I think before that we will have one more quiz. I think now is May 3rd, so I think maybe May 13th of May, maybe that will be our second quiz. May 13th, the Monday class, 1 hour. The quiz topic will be I think up until later we are going to see whether we are having the line integral and also the green theorem and maybe the curl and divergence, maybe up until that point. Okay? We are going to see next week what will be the topics for quiz. Okay, so quiz, 13th of May. Topics for sure, the topic is about the line integrations, okay? But not sure up until which part. So I think that depends on next Monday class. So that's information for quiz. So I think I will move to the next topic. Still related to the line integrals, I will finish off by today. So I will start with this fundamental theorem of line integrals. Before we see what we have in the theorem, let me just briefly recall. So let me write here. So recall. In calculus, especially calculus 1, we know that when we have the integrations of this f, capital F prime x, which means this is this first derivative of f with respect to x, this will be equal to, okay, this is a fundamental theorem in calculus. Let me write here, fundamental. Now we would like to make the similar conclusions in the line integrations, which we have the line integral is actually have two components, which is the del of f. So the function will be in terms of del. So let me show you what we have here, the theorem. So if the C is a smooth curve and it is given by the vector r, okay, and if we have the parameter starting from a to b, and then f also differentiable function of 2 or 3 variables, whose gradient vector or the del f also continues on the curve C, which means we can trace the del f with the projection on the curve C. So we can write the line integrations, the del f dot dr is basically a function of the vector positions at b minus f the vector positions are at A. So very particularly similar to what we have in calculus, okay, in the fundamental theorem of calculus, but here the functions in terms of the del. Okay, and remember the del means it's partial derivative, right? Just to let you know, this is practically if three variables, we have the partial x, partial y, partial z. Okay, so for the del. So this theorem, in summary, says that we can evaluate line integral of a, we call conservative vector field. Okay, we are going to learn more details, I think, later. Or we call last time this conservative vector field is the del, actually, or the gradient vector of potential functions. So the f we call as potential functions. Because we start by the vector field, and then we would like to know that if we can take a potential function f from that the gradient vector field, then we say it is conservative. So for example, let me just make it small here. If we look at the picture, we have two different curve. The first one is only for function of two variables. So this means this one, okay? So if f is function of two variables and C is a plane curve with initial point ax1, y1, and the final point or terminal point is b x2, y2. We can write this as the line integral, the del f dot dr, practically the difference in the potential functions. And similarly for three dimensions, for the space, we can write this as, I will just write the final results. Okay. Okay. Now to make sure that we get the theorem correctly, we can also prove this with a simple formulations. Now we can write this dot product as, so we can change the line integrations into the parametric, okay, parametric AB, and using the R as our vector positions, and change dr as r prime dt. And then we can take the dot product between the del and r prime. So del f is dou f dou x, and then multiply with the r prime, which is dx dt for the x-axis. And then for the y-axis, and for the z. And then dt. And basically, because since all these three components, they have the f, we can actually factorize and make it into a regular functions. But they are basically the first derivative with respect to t. So by taking the chain rule, we can write this as ddt of f of r. Which means that, I think you can see this, which means that the rough f becomes f prime, which has these three components, and then the inside functions we need to also derive and multiply with the chain rule, right? So it becomes dx dt and dx. Okay. And thus, by this integrations, then the derivative will be cancelled. So which means that we are going to plug in all the b and a as the differences. So f r of b minus f of r of a. Okay, that's, I think, what we have from the line integrals del f dot dr. So every time you heard something related to the fundamental theorem, especially in calculus, it's actually try to connect the derivative and the integrations. And within this notes, actually, another important point. If we have two curves, let me write here, just a notes. So if C1 and C2 smooth curves with the same initial points and terminal points, we can conclude that the line integral between those two curves, this will be the same, okay, equal. If we have different initial points or terminal points, it will be not equal. But here, within this conditions, because we only see the initial point and the terminal point, then whatever the curve will be, as long as it is smooth curve, differentiable, we can make this equal in both of the curves 1 and curve 2, if they are having the same point. Okay. So this is actually, I think we can say also, what makes the line integral or the vector field conservative, okay? Because it only depends on the initial point and terminal points. Okay? I will write in the next page of that notes. Okay, so if we observe that they are the same whenever the del f is continuous and they are only depends on the initial point and terminal point, we can say that they are independent of the path. Okay? They are not depends on the path they choose because of the initial points and terminal points. So let me write here to give you the idea. I think this will be, I will write first. Let me write some notes first, okay? Okay, whenever the del f continues, we observe that this can happen. So we say that line integrals depends only on the initial point and terminal point of the curve. In general, if f, capital F, is continuous vector field with domain D, then we say the line integral of f dr will be independent is, let me write, independent of path if the practically the one that we write before. Okay. For any two paths C1 and C2 in the domain that have same initial point and terminal point. And the theorem, it says that the f dot dr is independent of the path in the domain if the f dot dr or line integral f dot dr equal to 0 for every path. So we can actually rewrite this as, and remember that the curve can be cut, becomes several segments, right? So we can write this as curve 1 plus f dot dr plus the curve 2 f dot dr. So we can see that this is actually the minus of the part here. This is minus. So if you could see from the picture, okay, we start from this part here, which if we have two curves, the same initial point, terminal point, we can make this equal. So we can say that they are independent of the path. And if we can imagine that this curve is a closed curve, okay, then we can split the curve, becomes two different curve, which means that this will be from A to B, it's C1, from B to A, it's C2. So A to B can be C1 or negative C2 because it's opposite direction of the C2. So C2 is going to be, counterclockwise, but we need to make from A to B. So that's why this is becoming negative C2, and we can rewrite as a negative here, which resulting in basically 0 because they are going back into the same positions. Okay, if we continuously see the line. So every closed curve, we will have the line integral of the curve f dot dr will be equal to 0. So the only vector fields that is independent of the path, that is what we call the conservative. Okay. Let me write here, maybe this one here. So vector fields that are independent and of the path are conservative. If you like heard before the conservative, maybe in physics, it means that they are independent of the path. If you, I think if you can imagine the gravitational field or electric field, it's also conservative force field. So the work done by the field, and as it moves any object around, maybe we have some circulations, like maybe some curve, that will be zero. Because remember, this f dot dr, if you maybe imagine that this is like this. Like work is done by taking the force and then you are moving some distance, right? So it means that when it's equal 0, the work done by the f, or now in terms of factor, it's a vector field. It can be like a maybe magnetic field or electromagnetic field, which means that the work done by the vector field when we have the object inside, it will be equal to 0, okay, on a closed curve. Okay, so that is independence of the path. But I think we can make the theorem more generally more applicable, okay, because it's not always closed, but it can be also open for some parts of the domain. So we can write, I think I will write here, give you this part here. So suppose F is a vector field continuous on the open connected domain D. So if the f dot dr, or line integral, independent of path in the domain, then f is a conservative vector on that domain, so that the functions f, or the potential functions, will be exist such that the del f is equal to vector field f. So if we can we can prove this just with a simple observations. Let's say we have point, starting point AB is a fixed point on domain or D. We start by defining the function of two variables, taking the point from AB to xy, and this will be f dot dr. This is for any point in D. And since we assume that the line integral f dot dr is independent, so it doesn't really matter which curve or which path it is going to be taken. So does not matter which curve or which path is being taken from AB to XY. Now suppose that we have, for example, we choose this C1 and C2 as you can see from the picture. So we choose point x1 y with the x1 generally less than x, and C consists of any path C1 from AB to XY. Sorry, X1Y, sorry. And followed by, or maybe and taken C2, which is the only horizontal segments from x1y to xy. So we can write the functions curve 1 f dot dr plus curve 2 f dot dr. And this is basically, we are starting from AB and then ends in the curve 1 is x1y, and plus the last one is just the C2 and if you see this integrations doesn't depend on x. Okay, because we choose the point x1y, so if we derive partially with respect to x, this will be equal to 0 plus now suppose that if we write f in factor, let's say pq for each x-axis and y-axis direction. Now we can write this, as integrations p dx plus q dy. But in C2, the y is constant, right? So here is y is constant for C2. Okay, which means when we derive the y or dy, it will be equal to 0. So here, since on C2 y is constant, dy is 0. So this will be 0. So this part here becomes this is p dx plus q dy and equal we can exchange this with the C2 is x1 to x, right? This will be p, and then let's using the parameter t, okay, because we integrate with respect to x, and x is a variable and y is constant. So it's equal p xy. Okay, so actually what we are going to do here is basically we need to compare. Okay, so the first here, our curve. So so we have two curves actually. So the first curve, they have the same C1, but I would like to change this second C2, or perhaps a C1 is basically can be any smooth curve, but the C2, the first one will having a y constant, the second one is having x constant. Okay, so what's the difference? The difference is on the partially, when we derive partially. When y is constant, the partial for y will be 0. This one will be, for x will be 0. So if we compare and using the same structure definition, okay, by definitions, okay, by similar arguments, when we partially derive fxy, we will have this p dx plus q dy, and simply the dx will be 0. So this will be y1 to y. This is qxt dt, and this will be equal to qxy. So both of this resulted in terms of the p that is in the vector fields, or q, okay, when we derive partially with respect to x and with respect to y. So by the end of the day, what is the conclusions? Basically, we say that the conclusion is, it is true that the f is conservative, so that the f is basically is PQ or PI plus QJ in terms of vector. That is actually the partially derived for each axis. Or we say that this will be the del FF. So this is, we say F is conservative. Basically, this is just proving that the path is, we say it doesn't depend on the path. Okay? As long as you define the initial point and the terminal point. And the conservative, also, if you remember, in physics, one of the most popular formulation is the conservation of energy. That is why it's called conservative or has conservations, because basically it says that no matter how we start from and ends with any points, it will be the same. So that's why in thermodynamics, the energy is not being created or being released, because basically all the form of energy, they are the same. But so far, what we prove is basically only this we call the simple and connected domain. There will be several aspects if we perhaps change the D that will affect our formulation and theorem. Okay. Okay, let me get into how we could determine whether the vector field is conservative or not in practical way. And if the F is conservative, how we can find the potential functions. So usually, so vector field is, if you see the formula, is the capital F. Potential function is the small f. Okay. Okay. So based on what we have before, so suppose that if the vector field is pi plus qj, and suppose that if this is conservative, and p and q continuous, or okay. So how to find potential function f? I will okay, so let's continue to work on this. So the conservative fields, or conservative vector fields, and the potential functions, and basically how to determine the potential functions and how to make sure that it is a potential function. So first of all, if this is conservative, if the vector field is conservative, and the p and q, they are continuous or partially continuous, we can partially derive this p and q. We can write, okay, suppose that exists potential function in terms of vector fields equal del of the potential function f, and that is the p will be partially derived of the potential function with respect to x, and q will be dou y or dou f dou y. Okay, and then if you remember, if we take the second partial derivative, we can write, for example, for p, we derive again one more time with respect to y, and this become okay, which means in the partial derivative, we remember that the partial xy is equal to partial yx in the Clairaut's theorem. Okay. So basically we say that this will be equal to, if we change the order of the partial, okay, if we start from x and then y, or start from y and then x, for the same f, the result will be the same. So which means that this will be equal to, so as we can see that basically the dou y p is equal to dou x of q. And this could remind you to our differential equations in the engineering mathematics 1, that we can also find solutions for the functions when they have the same second derivative, right? So we can write as this theorem to officially write in more clear. This is basically the same. So if the f is a conservative vector field, okay, where p and q, they are continuous first order partial derivatives on domain D, then throughout that domain we will have the partially derived with respect to y of p. It will be equal to partial x of q. But this is actually works only for simple curve. or simple type, okay, curve. There are several types of the curve. If you can see from on the left, we have a simple curve but not closed, simple but closed. So simple means we can define easily the position. If it's not simple, it means that it has some loops that it can entangle with the other segments of the curve. And we call this not simple. And it can be not closed, not simple, so it's not connected. It can be closed but not simple, which means there are some entanglement in between. But all this stuff here, we say that the dou dou y b is equal to dou x cubed. It means that it only works for a simple closed curve, a simple closed curve. So simple means the curve doesn't intersect itself anywhere between endpoints. So we need another condition that can be more generalized and can be applied effectively. So we need to have what we call as a simply connected region. So simply connected region, this part, so this region means region which or let me write here, a connected region D such that every simple closed curve in the D encloses only points that are in D. So, which means that if we could draw the region, any region that is describing for taking some holes in between of the area, that it's not simply connected. Simply connected means in every restrictions or in every part of the region there is no hole, so to speak. Okay, so intuitively we can imagine this is like the full area with some area restrictions, that we call that as a simply connected region. And we cannot have, for example, if we cut and then it becomes two pieces, it also doesn't work like that. It needs to be in one piece, in one piece without any hole. That's what we call the simply connected region. So we need to have this as our region so that the theory works. Okay? So what is our goal here? We need to find the potential functions from the vector fields. And it will be applicable if it is conservative, or in a sense that the region, they are all simply connected. So we can write in more generalized this theorem number 6. I think more to this simply connected regions part, we can elaborate more, I think, after some subtopics. I think after this we can see. But I think now we can have some example first. Okay, so let me go through some simple example. So first is how to check whether the vector field's conservative or not. Basically, how to check is we need to prove that, so conservative is when the partial for P and Q, they are equal. So P is, so if we have the vector fields, always remember, by default, we state that this P will be in x-axis and Q will be in j-axis. Okay. So P is x minus y, which we can partially derive if we derive with respect to y of the P. So this will be, so for this is for A, for number A. So this will be -1, okay? Sorry, P. And for Q, we have x minus 2, which if we derive partially with respect to x is 1. So since this is not equal, so if this is not equal, then it's not conservative. So F is not conservative. So if you see the vector fields in this figure, this is for number A. The vector field has the exactly same direction with the curve. Okay, suppose that the C is the curve. So it seems that the line integral, so here, it seems the line integral f dot dr is positive or greater than 0. Roughly, okay, if we see that is because of the its point in roughly the same directions. Okay, the vector field point out the same direction as curve C, and that's why it's not equal to 0, or we can say it's not conservative. Okay. Okay. Now if we compare this part with the second curve here, by just seeing the curve, let me explain first a little while. You see how we have this for the curve 2, perhaps it is having the same directions with the curve, but the vector fields, it has some opposite direction. For example, here it's opposite directions, it's also opposite direction here, although the other part is having the same with the vector fields. But because of this, we can say that this will be canceling each other, which means the f dot dr will be equal to 0. Okay. Roughly, okay? But I think it's better if we compute. Okay? This is if we visualize. But I think sometimes the problem with looking at this curve, we need to make sure as close as possible to the vector field. How many units will be in between the vector fields? It also can help. But I think whenever you see any opposite directions and the other part is having the same direction with the vector field, you could sense that they will cancel. Okay? If you compare to the first part, they are going the same everybody, so they will not canceling in any way that you want, right? But of course, looking at the visuals, you need to make sure the direction. Make sure the direction. But to confirm, exactly to confirm how this can be possibly true, is taken this conservative proof. Whether these two partial is equal or not. If they are equal, it means that they are conservative. So we can do the same thing with the part B. So let's say, let me write again part B. F is 3 plus 2xy I plus okay. So we can start with taking this as P, this is Q. We take the partially derived with y of P. This will be 2y, and then taking partial x with respect for Q, this will be, oh, this is 2x, sorry. This is 2x. So they are the same, which means that they are conservative. So this means that the F F is conservative. So the first example is just to determine whether the vector field is conservative or not. Okay. The second part of the typical questions within this chapter, okay, aside from the first topics we encountered last week, how to develop the line integrals, equaling that to the parametric equations, or simply using x and y, depends on the situations. Now we have the fundamental theorem, which states how the vector fields become conservative. And the second part will be how to get the potential function f, okay, which we are going to see in the next example. Okay. So next example here, how to find the potential function f. Okay, if we have the vector fields, and this is the same functions with the previous example. So we know that this is conservative, right? So this is conservative, f is conservative. We have proven in the previous question. So now, since the del f is equal f, okay, that the partial x is 3 plus 2xy, or this is p, right? Or let me just write the partial x, maybe more clear. And partial y will be x squared minus 3y squared. And remember that if you do the engineering mathematics 1, this is precisely what we call as a partial integrations. Okay, so we do partial integrations. Okay, so let's say we integrate with respect to x. Okay, so this will be f xy. So 3 becomes 3x plus, we only integrate the x, which means it's become x squared over 2 multiplied by 2 is become x squared, and we treat y as a constant. Usually we have added the constant, but since y also a constant, then this will be a function of y. Okay, okay, maybe this is a little bit familiar with the previous semester, right? And then taking the partially derived with y, so we get the partial y, right? So this will be partial y xy, and this will be 0. This will be x squared. So we derive y, and this will be g prime y. And this is going to be equal with this, okay? This is practically similar method as the previous semester. So we could see that the g prime y is negative 3y squared, okay? Which if we take the integrations with respect to y, gy becomes, so integrate, it's become negative y cubed plus some constant. So the f xy 3x plus x squared y minus y cubed plus, let's say, k, or maybe if you want to write c is okay, but I would write k. So this will be the potential function. So k is constant. So you can have two choices. Okay, you can start. So if you have partial x, you integrate with y, or you have partial y, integrate with partial x, and then later you partially derive with the other variables, and then it will be equal for each one of them. Either way, it should be the same result. If you want, you can go here, integrate with respect to y, which means you have the y cubed, and this will be 0, so y cubed something something, and then we can derive with respect to x, and then equal to the partial x. So maybe if we want, I think we can also develop. Let me write different color, so we can try to take the partially integrate with respect to y. So this will be x squared y minus y cubed plus let's say h of x, okay, as a constant, and then take this partially derived with x, that this will be partial x, this will be 2xy and 0 plus h prime x. Okay, so h prime then becomes equal to 3, or hx is 3x plus let's say h. Okay, so the fxy is 3x plus x squared y minus y cubed plus h. So h is constant. Okay, the same, right? Okay. Now last two examples. Okay. I think we can have review on Monday class. Okay. So far what we have learned and how to have some practice problems. And oh yeah, as you know, I think I've mentioned in the early class, May 13 will be quiz. The topics we can define or discuss next Monday, okay? Next Monday. Okay, now another examples. I think just a few examples, and then we can finish the class. I think we can finish early. So if we have this f, the same f as the previous examples as well, so we know that this is conservative. And we have the curve C, we have the vector R given by that equations, and we need to evaluate the line integral f dot dr. Okay, in the previous example, we know that the potential functions is equal 3x plus x squared y minus y cubed if we choose the constant as 0. If we choose constant is 0, or choosing the constant as 0. So as we know, since the conservative means independent, I mean right here, independent of the path, which means we need to pinpoint our initial. Okay, so initial start from 0, this is initial, and terminal point is when t is equal to pi. So we know that if we plug in 0, this will be 0, 1, right? Because sine will be 0, so r pi will be sine pi 0, so 0 and negative e with power of p. So we have these 2 points for initial and terminal. Remember that the line integral f dot dr we can rewrite as the del f dot dr and equal the f. Suppose that this will be the r1, okay, minus, or yeah, maybe let me write this r1 and this r0, or let me write this is r0, this is r1, or this will be 0 e negative e with power of p minus f of 0, 1. So plug in this point into the potential functions. So this will be equal to so negative e, because of cube it's negative, multiplied with negative it's positive, so positive 3 pi minus, if you plug in 0 for x is 0, so negative 1. So negative 1, negative, so it's negative 1. So this will be e power of 3 pi plus 1. It is much more short and straightforward because we only care about the initial and terminal point. Another method that we can think, since we have the r and we have the initial points and the terminal points from the parameter, the other point of view for the solutions is we can make another curve. Okay, so alternative solution. So since c is from 0, 1 to 0, negative e with power of p, then c can be described with any curve. Okay, c can be described with any curve and suppose that we have another curve. Let's say the curve is calling this negative tj. Okay, so we only care because they are on the same x equals 0, so we only have different variation in terms of y, right? And it starts from 1 or negative 1 to e with power of pi, because if we plug in into the r, it will be the same thing, right? It will be the same as we say the point starts from 0, 1 to 0, negative e, negative pi, or negative e pi. Okay. And we can use this curve in our line integrations. So we can take this as from negative 1 to e with power of pi of. So this is if we want to solve using the parametric, but I think the difficulty here is we need to think what kind of R that can simply say that it is the same as the original initial point and terminal points. We need to think how to write a new curve that actually has the same initial point and terminal points. Because it's conservative, the curve can be anything. We can design our own curve to help our calculations. Okay. So that we can write and solve the line integrals in parametric t. Okay. So we can use this R using the same point here, and then the f or the vector field we can using each one of t for R. So this become I forgot what is the f? 3 plus. So we can use the R of t is actually negative t, right? And the f is 3 plus 2xy I plus. Okay. So we can plug in everything. So x is 0, so this will be 3 minus r prime t is negative j, right? So we can write here 3i minus 3t squared, okay, because x is 0, right? Dot the negative j and then dt. There is no x-axis, so that becomes 0. So we only have the 3t. Oh, this is j. Sorry. So dot product. This will be 3t squared dt, or t cubed from -1 to e to the power of pi, and we get the e 3 pi plus 1. Same results. So this is actually what we have. So the original curve, which is this curve R here, et sine t, et cos t, that is the red curve. So this is et sine t and this is our new curve. Remember, this is vector functions, okay? So it's only having the line segments on y-axis. So far, this is function of 2 variables, but it also works with function of 3 variables as this example, but this example 5 here. But I think I will just stop until here and continue and have some overview for this chapter so far on Monday's class. Okay. So I think I will stop until here.